Welcome to Basic Power System Analysis using PSSE. In this lecture, we are going to discuss dynamic modeling of excitation system. First of all, what are the functions and performance criteria for a excitation system? So, a typical function of an excitation system is to provide the DC current to the synchronous generator field winding and to perform control and protective functions essential to the satisfactory operation of the power system. As we discussed in the previous lecture, our physical construction of the generator is like this. You have stator winding. Within this stator winding, you have a rotor. In this rotor, you have this field winding, which is energized with the help of DC current. So this DC current is being provided by the excitation system, and this excitation system basically controls the flow of this DC current in order to control the number one, reactive performance of the generator or the flux of the generator, and provide the protective capability. So the performance requirement of the excitation system are determined by the generator consideration, the supply and adjust field current as the generator output varies within its continuous capability. We saw that a generator typically operates between a generator capability curve, and the generator capability curve has two values: the overexcitation region and the underexcitation region. In the overexcitation region, you have Q max value, and in the underexcitation region, you have Q min value. So the generator is to operate within this region. And how do we control this reactive capability? This is controlled with the help of adjusting this field current. Secondly, the response to the transient disturbance with field forcing consistent with the generator's short-term capabilities. The next thing that can happen is, that was the steady state operation. That in steady state operation, you see that the voltages, my voltages are decreasing on the terminal voltage. What you will do is you just increase the flux in the system. So this increase in flux increases the induced EMF into the stator, and on the terminal voltage you get some higher value of megawatt. So this way you control the voltages in the steady state operating range. But in dynamics, what happens when you have zero voltage on the terminal? Now when you have zero voltage on the terminal, the exciter is going to provide its maximum current to the rotor, and with this maximum current being provided to the rotor, a huge flux is going to be generated, which is going to be Q max value. A higher Q max value is going to be generated into the system. So now this huge inrush of field current into the field winding can cause rotor insulation failure due to high field voltage, rotor heating due to high field current. So now this excitation system has to take care of this thing, that if you have high voltages, high field voltages, this should not cause the insulation failure. Similarly, when a huge current flows into this rotor winding, this should not lead to heating of this rotor winding. On the other end, what can happen is that when the generator is operating in the under excitation range, in under excitation, we are going to reduce the field current, and this reduction in field current can cause the heating effect in the stator. So we need to make sure that stator heating due to high var loading is not happening. Similarly, heating due to excess flux is not there. So the stator heating can happen both in the overexcitation range and in the underexcitation. So we need to make sure that in both cases we do not end up heating our stator. Similarly, heating due to excessive flux is not there. And on the power system consideration side, this was the generator consideration. On the power system side, we want our excitation system to contribute to effective control of system voltage and improvement of system stability. How this can improve system stability? You saw that in our basic transient stability studies, that when after post fault analysis, my generator was continuously oscillating. So if P electrical is oscillating, it means that the voltage in the generator will oscillate. When the voltages in the generator will oscillate, this can be controlled with the help of this excitation system. So that whenever the voltages are oscillating towards lower side, our excitation system can improve the voltage by increasing its reactive power. Similarly, when the voltages are increasing, excitation system can perform the reverse action in order, so it can compensate for the continuously changing voltages. Typical elements of excitation system consists of, so this generator, this is the electrical electrical part of the generator, which has all the flux intensity and the XD values, or the transient or subtransient these impedance values. So how does this interact with the exciter? So you have this exciter. Exciter is controlled by the regulator. So what happens is that at the terminal voltage we are getting some input from the exciter. So what will this exciter do? So what will this exciter do? This exciter will provide the feedback to the regulator, and the regulator will see, okay, whether my field current is more or my field current is less. Based on this value, my regulator is going to change the field current, and this field current will be provided to the exciter, and then this exciter will provide excitation to the generator. And some secondary controls available in the exciter are the power system stabilizer, which is helpful in stabilizing the system or reducing this oscillations in the system. Then we have this different kind of limiters. The limiters can be this over excitation limiter, under excitation limiter. These are the kind of limiters, or this flux limiter. So these kind of limiters can be there. And then we have this terminal voltage transducer or load compensation. So these are the different kind of things we have in a typical excitation system. So exciter provides DC power to the generator field winding. The regulator processes and amplifies the input control signal to a level and form appropriate for control of the exciter. As I told you, it is going to take the feedback, and it is going to make sure that the value provided to the exciter is appropriate. So it should not be high or less, so it is going to continuously do the process for it. So the terminal voltage transducer and load compensator senses the generator terminal voltages because it is getting the feedback from the generator terminal voltages, rectifies and filters it to DC quantity and compares with the reference. Load compensator may be provided if desired to hold voltage at a remote point. So now you have seen that a typical generator is connected to the system with the help of a step-up transformer. Now there are 2 points from where you can control the voltage. The first point is the generator terminal voltage itself, which is the LV side of the step-up transformer. Or you may want to control the voltage at the HV side of the transformer or the transmission side of the generation. So if you want to control the voltages at the remote bus, because this transmission bus is not the bus where this generation is being generated. So if you want to control the voltage at the remote terminal, then you will be requiring this load compensator. So the power system stabilizer, as I said, it provides additional input signal to the regulator to damp the power system oscillations. Limiter and protective circuits ensure that the capability limits of the exciter and generator are not exceeded. And what are these limits? Over excitation limit, under excitation limit, flux limit. There are various types of excitation system, but they can be classified into 3 broad categories. So your excitation system can be DC excitation system. In case of DC excitation system, what will you have? You are going to have typically a DC shunt generator available on the same shaft as the generator itself. Generator, prime mover, and this DC shunt generator will be on the same shaft, and this DC generator is going to provide directly the DC excitation to the exciter. Another form can be AC excitation system. So what is this AC excitation system? In AC excitation system, instead of this DC shunt generator, you either have a AC shunt generator or you take the input from the generator terminal voltage itself and rectify it into DC and provide it to the field winding. Or the third type can be the static excitation system. So static excitation system is usually this rectifier which takes the input from the station load or from the station auxiliary load, and from the station auxiliary load it converts its AC into DC, and then this is provided to the field winding. And this is the whole system of the exciter, so showing the everything. So here we have this exciter. This exciter is going to be connected to the generator with the help of field windings, and then this exciter is connected to the excitation system stability circuit, then the maximum excitation limiter, then the under excitation limiter, then the flux limiter, and all these inputs are being provided to the AC regulator, and this AC regulator is going to see what is the output of the generator, and based on this generator it is going to give the input to the exciter. And then we have this secondary control from the power system stabilizer, and this stabilizer is going to provide the input to the regulator also. This is going to be the additional input to the regulator to make sure that we reduce the oscillations in the system. As far as the dynamic performance of the excitation system is concerned, the dynamic performance of the excitation system can be checked like this, that this is the steady state value where the excitation is operating in steady state, but we want to see the dynamic performance. So what will happen in dynamics? When the fault come into the system, voltage will become zero. So now the terminal voltages are zero. Excitation system is going to, or the regulator of the excitation system is going to sense that we have zero voltages on the terminal, but the input, the reference input is some other value, say 1 per unit or 0.9 per unit. So when it sees the difference, it is going to inject the full power to the excitation system. So as a result, what is going to, so this, after sensing the voltage difference, so after some delay, it is going to, the excitation system is going to react to the zero voltages, and it is going to increase its reactive power. So this increase in reactive power is going to depend upon some kind of a rise time, which is going to be in the form of some time constant. And when it reaches its maximum value, it is going to basically overshoot. Then it is going to adjust its value and try to find a value until it reaches some steady state value, new steady state value. So this will be my settling time, where I, as soon as I get into my this specified band of this exciter within the steady state value, this is my value known as the settling time. So this is my settling time, this is my peak value, which is the maximum overshoot which has been attained. So the overshoot will be equal to the steady state value minus the overshoot value. So this way we monitor the dynamic performance of the excitation system. In simple words, what we want from the dynamic performance is that whenever the voltages or there is a fault in the system, the excitation system should react and provide maximum reactive power output to the system so that it can compensate for the zero voltages. In the same way, how the dynamics is shown. So if we consider this as a black box, there are different, there will be different inputs. So the one of the important input will be the terminal voltages. Then we have going to be the compensation voltages. Then there are going to be different kind of inputs: the over excitation limit voltage, the under excitation limit voltage, the voltage threshold, or so different kind of excitation protective limiters are going to be provided. And the output will be simply one thing, which is known as the feed voltage. So these are the inputs, these are the outputs, and these are the different parameters we have to provide for the different constants, or the different parameters we have to provide for the excitation system. So from where you can get these values? These values are typically provided by the manufacturer of the generator. So the generator manufacturer is going to provide you with the model or the type of the excitation system, and what is going to be the control model of this, and based on this control model he is going to provide you with these values. But if the manufacturer has only provided you with the model name or this diagram and it has not provided you with these parameters. What you can do is you can use IEEE standard 421.5 2005. So this standard provides you with some sample values of the excitation system. So from there you can get the parameters. And what are the how we are going to provide the diary file for specifically this IEEE type ST1 EXST1 system. So this is the syntax. So we will use the same syntax to provide the to prepare the DYR file.